Section 6.2, Orthogonal Sets. Let's start off with a definition here. A set of vectors u1 through up in Rn is said to be an orthogonal set if each pair of distinct vectors from the set is orthogonal. That is, if you take the dot product of them, you get 0 for any two vectors that are not the same vector. So let's do an example. Here we have three vectors, v1, v2, and v3, and they want us to know if this is an orthogonal set. So what we want to do is we want to take the dot product of these two, or the inner product. So remember, the inner product is actually a matrix multiplication where you take the transpose of the first vector and matrix multiply with the second vector. So that's essentially equal to the transpose. So that would be just 3 minus 3, 0, and then that gets multiplied by v2. Now you probably don't need to do this because you can basically do this product. So this is really just 3 times 2 plus minus 3 times positive 2 plus 0 times negative 1. So we would get positive 6 minus 6 plus 0, so that's going to be 0. We can do the same thing over here, but I actually have MATLAB running, and if I take a look at v1 defined as a vector, it's a column vector. If I take v1 multiplied, or taking the dot product with v2, this isn't going to make sense for us because this is MATLAB's trying to do a matrix multiplication, so we have to actually use the definition given here, and that is to take v1 and the transpose of that. Remember, the transpose is an apostrophe, and then multiply it times v2, and here we get 0. So if we do the same thing, v1 transpose times v3, we'll check that that's also equal to 0, and v2 transpose times v3 is all going to be 0. And if you switch to order, it's still going to be the same, so it's going to be zeros. So we have 3 vectors, and to figure out how many times we have to take the dot product, we're just looking at combinations and pairs of each of them. So here we have 1, 2, and then 3. So there's 3 dot products that we have to perform. We don't have to perform the commutative property because v3 and v2 is equal to v1 and v3, and so it would be a good idea to be able to count how many dot products you have to perform in order to check if a set is orthogonal. Okay. Still in section 6.2. This is part 2. We have a theorem now here. Suppose we have S is a set of vectors, and it's an orthogonal set of non-zero vectors in Rn. Then S is linearly independent, and hence is a basis for the subspace spanned by S. Okay, so that's the theorem. We're not going to prove it, but you can check the book for the proof. The proof isn't so bad because if these are all orthogonal, then they're not going to be linear combinations of each other. We can do that by assuming that it is orthogonal, or it is a linearly dependent set, and then showing a contradiction. That's what the proof in the book does. Anyways, we're going to use this to show that if we have 3 vectors in R3 that are orthogonal, which we've shown in the last part, then they span all of R3. So if we have an orthogonal set, then the set is actually linearly independent. We can show that they're linearly independent by, setting them up as a matrix and showing that it reduces to the identity. You can set them up as a row or column matrix. You can do a variety of things. Looking back at the inverse matrix theorem. Anyways, if this is in fact a set of linearly independent vectors that span all of R3, then we should be able to express any vector in R3 as a linear combination of v1, v2, and v3. And so this is what they're asking us to do, is to find x in terms of the basis vectors v1, v2, and v3. So that's what we're going to do. So we're going to write, maybe to begin with, our basis, or our vector, should be a linear combination of these things. What does that mean? If you remember linear combination, it says that the first vector has a scalar of c1 plus the second vector with a scalar of c2 plus the third vector with a scalar c3 is going to equal to this, and we should be able to find solutions for this. Okay, so there are several ways to do this. One way is to write this as a system, and then we can write it as an augmented matrix. So we have v1, v2, and v3 already, so let's let our matrix A to equal to v1, v2, and v3, so that we have the matrix here. And then let's let this fourth vector be b. So b is going to equal to 5, and then it's a column vector, so let's write it with semicolons. And so we can say the augmented matrix, let's call it AB, is going to equal to A and B, so that we have a 3x4 matrix. And then we basically want to reduce. So this is a quick way of doing it, of course. Otherwise, you'd want to do it by hand. So our REF, we're going to get x1 is going to equal to 1 and 1.333. So I think that's 1 1/3, and then we have 1/3 and 1/3. So it looks like we have values for these things. So C1 should equal to, let's call it 4/3. C2 would equal to 1/3, and C3 would equal to 1/3 as well. Okay, so that's it. So the next part goes beyond the orthogonal set and asks us to look at an orthogonal basis. So an orthogonal basis for a subset W in Rn is a basis for W that's also orthogonal. So remember that if you have a set that's already orthogonal, then they must be linearly independent. And so if they're linearly independent, they must form a basis. So this is just the definition of an orthogonal basis. And we've already been dealing with it, and so this just formalizes the definition. Now we have a theorem that says if we have a set of vectors u1 through up, and it happens to be an orthogonal basis for W, then each y in that subspace W can be written as a linear combination of the basis. So that's what we did before. And but not only that, but here they give us the formula. So the formula for this is going to be the jth weight of your linear combination is going to be the dot product of the vector dotted with the jth basis vector divided by the dot product of the jth basis vector with itself. So if you remember back, we had, I think it was 4/3, 1/3, and 1/3 for C1, C2, and C3. So let's see. Let's rewrite this a little bit just so we are using the correct letters in our formula. I think this is y. This is y, some vector within the subspace. And then instead of v's, they happen to use u's. So if you want to change that to u's, that would be fine as well. And so we can use this formula to find our C1, C2, and C3. So this is our y vector. This is U1, U2, and U3. And again, that comes from a linear combination. So according to this, our C1 should equal to this set of formula, or this combination of formulas where you're looking at the first vector 1. And if you do that, we're essentially taking the dot product of U1 with y and U1 with itself. So let's see. Let me just set up a fraction for us here. So y is equal to this. So we want this thing, and then dotted with this vector, and then it's this vector dotted with itself. So let's see how that's going to look like for us. The first dot product, if we combine this, it's 15 minus 9. So that's positive 6 plus 0. So this would be 6. And then we have 9 plus 9. I'm sorry. Let's try that again. This is 15 plus positive 9. So 15 plus 9 is 24. And then we have 9 plus 9, that's 18. Okay, and then if we reduce this, I think these are all divisible by 3. That's 8 over 6, I guess 6. So that's 4 over 3, which is what we got earlier. So that's C1. We can also figure out what C2 is equal to. And this is C2, 2 and 2. Now we already have these things in our MATLAB, so we can just try to figure that out. And remember that B is that like that Y thing that we're looking at, and then V2 is that U2 that we're looking at. That's 2, 2, negative 1. So let's do the computations. So B transpose times U2 is going to be the numerator. Oops, I'm sorry. That's B transpose times V2. And so we're going to get 3. And then V transpose times, or V2 transpose times V2 is the denominator, so that's 9. And that is 1/3, which is what we got earlier, and then we'll finish it up with trying to figure out that last one. So with 3, and 3, so that would be B transpose times V3. That's 6 divided by, and then V3 transpose times V3. 18, so that's 6 over 18. 6 divided by 18, which again is equal to 1/3. And that's those are the exact same coefficients that we got last time, except we didn't have to do the row reducing. We simply had a formula to use where we're looking at dot products of things. All right. Next is orthogonal projection. So the idea behind orthogonal projection is that you're given two vectors, y and u, and you want to project y onto u. And so here they come up with another vector v, or z, and another vector alpha times u, which they'll eventually call y hat. So what they want to do is they want to scale u so that it has the length of a line that's parallel to u, but then it goes as far as a perpendicular drop from y. So that is y hat is alpha times u that's been scaled, and z is going to be a vector now going from y hat to y, so that z is actually equal to the difference of y hat, or y minus y hat, so that z is perpendicular to u. So they derived the formula for these things where if z is in fact perpendicular to u, then the dot product is equal to 0. And so what we get there is a formula for the scaling factor. This is how much we need to scale u by, and then if we take that and multiply it by u, then we're going to get the y hat value. So a, or alpha, is a scalar, and sometimes that's called the scalar projection of y onto u. Y hat is the actual vector, and so that sometimes is called the vector projection, or the orthogonal projection of y onto u. And then z now is a connection between y and y hat. So z is sometimes called a component of y orthogonal to u. So it's not y, but it's going in the y direction, and it's perpendicular to u. So here's an example. Suppose y is equal to 2, 6, and u is equal to 7, 1. Find the scalar projection, the vector projection, the component projection of y onto u. And then we were to describe this graphically. So if we just follow the formula, we can get the scalar projection by doing this dot product. So that's equal to let's see, it's y, so we need the transpose of this dotted with this. And then we have this dotted with itself. And so this is going to equal to 14 plus 6, that's 20, divided by, this is 49 plus 1 is 50. So 20 over 50, I guess that's 2/5. And so that's a scaling factor. Now if we want to figure out what u is equal to, or what y hat is equal to, y hat is going to be equal to, this is a formula for y hat. So this is 2/5 times our vector u. So if we scale this vector u 7 over 1 by 2/5, then we're going to get that vector. And then, so this is the vector projection and the orthogonal projection. The component of y orthogonal to u is essentially going to be the difference between them. So that's z is equal to equal to that, and y is equal to 2 comma 6, and then we found y hat, which is equal to this. So I suppose we can work this out, but we can just keep it like this for now. I do want to take a look at the graph of this, and for this we'll take out a different program, graphing calculator program, and here we have the vector going higher over here is a vector y, and then our vector here is u. And so let's figure out what this vector is going to look like. And so I need to draw my vectors, always starting from the origin, and then with a comma, and then another vector. So this is going to be 7, 1, but it's being multiplied by 2/5. So if we look at this carefully, let's zoom in a little bit, we have our vector here, that's a red vector, and that red vector stops, it's going along u, but it stops over here, it stops somewhere. So let's take a look at this vector over here, the 2, 6 minus this thing. So again, these vectors have to come from the origin, and we'll talk about adjusting this in a minute. But here is the vector I want. Oops, I think I want something else before this. So I want 0, 0, comma, and then 2, 6 minus this vector. So this is the blue vector over here now, and the blue vector is a vector from the origin. But if we don't want it coming from the origin, if we want it coming from, say, this vector, this point of the vector over here, which is 2/5 times 7, 1, that's the point where it comes from. So we can actually translate this vector. It gets a little tricky now, but let's see it translated. So to each of these things, I want to add this vector here. So this is plus. So technically, this is what's happening. But if you notice that 0, 0 plus this is just going to be that, so I can essentially get rid of 0, 0 if I wanted to. And then these two things would equal a 0, so it's just 2, 6. So if we take a look at that, we'll see that that's that z vector that they were looking at. So the blue vector and the green vector are essentially the same, except the green vector has been translated away from the origin. Okay, so basically this drawing, we have the u vector, we have the y vector, we have the z vector, and we have the y hat vector, a vector that goes only this far. Okay? All right. Now, notice that the length of u didn't matter in this case. In fact, if we have any line going through the origin in the same direction as u, then that would work also. We would still get the same answers. Our answers will not change just because the length of u changes. And so technically, you can see this projection of y onto u for any subspace. So in other words, if we had any other vector u, so regardless of which way we go, how far we go, we can actually take a look at this line. So we can have it go the other way or whichever way, but in any case, we can see this y as a projection onto the subspace that's spanned by u. And then, so it doesn't matter what u is equal to. in this case, our y hat is always going to be the same y hat value, and so we're going to be getting the same z value as well. Now we move to orthonormal sets. So remember that orthogonal sets are, when they're perpendicular, a set is orthonormal if it's a set of perpendicular vectors that are also unit vectors. And so unit vectors just means it has length 1. So if W is a subspace spanned by such a set, then we say that we have an orthonormal basis. So instead of just orthogonal, we have an orthonormal basis. So these are automatically linearly independent because we know that it's orthogonal, it's linearly independent, and the added condition is just that we have to have unit vectors. So our first simple example of an orthonormal set of bases are the standard basis vectors. They're orthogonal, and they each have length 1. So let's go back to our example. We had a set that was an orthogonal set, and we said that these are 3 vectors in R3 that are linearly independent because they're all perpendicular, mutually perpendicular to each other. And so is this an orthonormal set? Well, if we try to figure out the length of these things, so we say note that the length of V1, so what is the length of V1? So we have to write it as a length of V1. And remember that this is the square root of the dot product with itself. So this is equal to the square root of V. That would be a vector V C dot V. So we take the dot product of this with itself. We see that this is 9 plus 9 is 18, so that's a square root of 18, which is clearly not equal to 1. So it's not an orthogonal set. So all we have to do is divide this out by square root of 18, then we would have an orthogonal set. So what we can do is let U, instead of V1, we're going to let U1 equal to the square root of 18, or 1 divided by the square root of 18. Times this vector, then we would have a unit vector. So let's see if that actually works. So our V1, let's take a look at our V1 again. Let's multiply this by 1 over the square root of 18. So let's let U1 equal to 1 divided by square root of 18 times V1. Let's use the times. And then we get this, and so we want to take the, we want to figure out what U1 dotted with U1 is. That's U1. U1 dotted with U1. And remember, the dot product is really a matrix multiplication with a transpose. And we get 1. Oops, what happened? There we go. We get 1. So if we were to try to find the length of U1 here, you're actually going to get 1. So that's the same thing's going to happen here. All we need to do is we need to figure out what the, take the square root of the magnitude of this. So we can find U2. So U2 is going to be this vector divided by the square root of the dot product. So the dot product with itself is 4 plus 4, that's 8, plus 1 is 9. So square root of 9, I think that's 3. And so let's double check and create our u2 vector is going to be equal to 1/3 times the v2 vector. And so if we try to find the length of that, or the dot product with itself, technically you'd have to take the square root, but if we know that the dot product with itself is 1, then the square root of that is going to be 1 as well. And so we have u2 is equal to that, and then u3, let's see, oops, let me copy this again. So u3 is going to be 1 over the square root of something times u3, which is 114. So 1 plus 1 plus 16, so that's 18. That's the same denominator that we had up here. So let's construct our u3 vector, which is going to be equal to 1 over the square root of 18 times our v3 vector. And I don't know if that's going to the magnitude of this is going to add up to 1. Let's see. u3 prime and u3. Oh, it's equal to 1. So we do have unit length. So now if we have this set of vectors, then this set of vectors u1, u2, and u3 is going to be an orthonormal set. So remember that v1, v2, and v3 were already orthogonal, so all we have to do is normalize each of them to make sure that they're orthonormal vectors. So they're orthogonal and have unit length. Okay. The last part of section 6.2, we can take a look at a couple of theorems and a definition. So theorem 6 says that you have an m by n matrix U that has orthonormal columns if and only if U transpose times U is equal to the identity. That's an interesting fact. So let's take a look at that. Without really proving it, let's take a look at it based on an example that we had. We had a set of vectors here that was orthonormal, u1, u2, and u3. And these are vectors that can be expressed in MATLAB with decimals. And we had that already. And it says that ut, the transpose of this vector, or this matrix times itself, should equal to the identity. So let's create a matrix U that's going to equal to u1, u2, and u3 as its column. So here's our matrix U now, and the transpose of this is just the transpose. The rows and columns are switched. And so if we take U transpose, multiply that with U, we should get the identity. Now there's some negative zeros here, but that's just going to be 0. And we see that we have 1s in the diagonal, and so that's the identity. That's pretty curious. Let's see if we can multiply it backwards, U times U inverse. So we get the same result. So I think that leads us to this definition down below here already, where it says if you have an orthonormal square matrix, then the transpose is equal to the inverse. So that's an interesting fact. So there are other interesting facts about this. Let's backtrack to Theorem 7. It says here that if U is an m by n matrix with orthonormal columns and x and y are vectors in Rn, then the length of U times the vector is equal to the length of the vector itself. So that's an interesting fact that says that if you have a length here and you multiply it with an orthonormal matrix U, then its length is going to remain the same. And also the dot product of ux and uy is going to equal to the dot product of xy, and then that's only going to be equal to 0 if the dot products of these things are equal to 0. Okay, so let's take a look at that x that we had earlier, where x is equal to this vector, and we were able to write it as a linear combination of the v vectors, but we certainly can write it as a linear combination of the u vectors as well. But let's take a look at the length of this thing. So the length of this vector, let's use the notation here, the length of x is going to equal to the square root of, let's see, this is 25, 25 plus 9 is 34, 34 plus 1 is 35, so this is the square root of 35. So if we take this u vector that we found, the u matrix that we found, and apply it to this vector, then the length of that should also be equal to 35. So let's see, the u times x is equal to, and then since u is kind of this complicated looking matrix, instead of doing it by hand, I'm going to use MATLAB to do it for me. So I have my U matrix, remember my U matrix, and I think this was called my B matrix way back when. So U times B is going to be a column vector that looks like this. Let's call that C, or UB. Let's just call it UB. U times B. So this is our UB matrix. So that's basically this U times X. We can write it out if we want, I suppose. So after we do that dot product, 1.7712, and then we have a negative 5.2998 and 1.9428. So now we want to find the length of this. So the length of this, let's get the notation down, ux, and so here it's called ub, so ub, so the length, remember, is a square root, so square root of ub dotted with itself. So that's equal to 5.9161. Well, we should have just taken that without the square root, but let's take the square root of 35. And we see that we get the same thing. So this must be equal to the square root of 35. Okay, so we see that it didn't change. This isn't a proof, this is just an example of part A. We can find examples of parts B and C, but these are good formulas to remember if you're dealing with an orthonormal, with an orthogonal matrix. That's orthonormal. It's defined as an orthogonal matrix, but I think it's better if we call it orthonormal so that we know that it's orthogonal and it also has unit length columns. All right, so that's the end of 6.2.